Checking input levels. That should be a bit better. So what's going on? Here's me logging in to my cluster. So this is how I log into my cluster. And you can see you're greeted by Arturo Prat, and the name of the cluster is Esmeralda. I'm looking into expanding the cluster these days because I just won a research grant. Well, actually, two research grants this year, which will allow me to significantly expand my cluster. And I'm looking into, together with some compute nodes and doing some AI stuff, what I want to do is the network, probably upgrade the network and have a more serious long-term storage solution. But what this video is about is the fact that I installed open code on the cluster, and this is my modified version of open code because we're calling it Ladruño AI Labs. The thing is, I have an agent system running in my cluster, and I can ask some questions to this thing, and this is running Big Pickle, so I'm not running an AI model in my cluster. I am running it in the cloud, but this thing has control over my cluster, which is fun. So what I was doing is I wanted to benchmark the network, and to that effect, so here's my little session. So what I told open code is, oh man, this is so huge, all the way up here. You're in my Esmeralda cluster, HPC cluster made out of blah, such and such. What I need to do is a comprehensive benchmarking suite for this cluster, and I need to evaluate whether the network and I/O input output are bottlenecks, and also get a sense of how well I'm using the CPUs, blah, blah, blah. There's a lot of stuff. So I gave this thing access to everything, and it started figuring out some things. I had to give it some directives. But it went in and it ran some stuff in here. And I want to show you, before I continue with this, what did this guy do? What did this guy do? So over here, I'm gonna, okay, let's exit here, and I'm gonna go in the cluster with my regular user. I have a master and there's some benchmarks folder. So this is all created by OpenAI. It went in and it created all this stuff. And so it's running a bunch of benchmarks. So if I go run all reviews.sh, it's going to be running this all reduced benchmark. What's the all reduced benchmark? I can BI that, and let's say MPI all reduce. The nice thing is that it went directly for C. It's not goofing around. It's not going into Python mode or anything like that. It went and wrote this C for me. And the main thing here, this is an all reduced benchmark. So what does that mean? It means that it calls this MPI all reduce intrinsic. I've never seen this code, but I know a little bit what it's about. So it's testing the network at different levels. And this all reduce is an operation where you send a bunch of data across the MPI processors, and all the processors together do a reduce operation. Let's see if there's another benchmark here that I can use. So the MPI all reduce benchmark. Let's see what else is here. Let's go. Oops. Like this. The broadcast, which one? The ping pong one might be easier to explain. So the ping pong benchmark, what it does, it's using MPI, where is it? Send and receive. So each rank, so you have a parallel setup, and it's spinning up a pool of processors, and I guess in this case the odd ranks are going to be sending a message to the even. So sorry, the even ranks are going to be sending a message to their partner, and their partner is gonna be, I guess this partner, where is it? Where's partner defined? It's gonna be the next odd processor. Anyway, so rank 0 sends to rank 1 a message and then receives the message back, and then the message size is something that varies, and then you can get a sense of how the network is working with a MPI. Anyway, you might be reading this. What did it find out? It found out for different the latency. It measured the latency and it measured the bandwidth for 2, 4, and 8 nodes, and it found the latency for 2 nodes, and yeah, this looks pretty good, like 122 microseconds for 2 nodes. But then as you go up for 4 nodes, and in this case node is how many computers I'm using, and it's going all the way up to 8, and the latency goes down and the peak bandwidth goes up as the number of nodes go up. So the key finding for it is that for 4 and 8 nodes, the results converge at the expected rate for the 2.5 GB internal network that I have there. And this doesn't, it's not the 10 GB network, which I don't use it for the compute. I'm not using that. So this is consistent with the setup of the cluster. And then the collective rank, what is this doing? All reduced saturates at this. The tree algorithm is bandwidth limited at 2.5 GB bottleneck. The bottom line is that the 10 GB Intel NIC, which I didn't tell anything about it. It found out all the hardware that it had. It just went crazy and started using the cluster and figuring out stuff all by itself. So these links are the nodes, the compute nodes are talking over the 2.5 GBE link, which is exactly how this is configured. So let's do something else here. Let's quit NeoVim, and I'm gonna keep track here of what OpenCode is going to be doing in the cluster. So let's run this command. Bring the font down a little bit. So this is what's going on right now in the cluster. There are a few things that are pending. There's something running, something else running. So this is one of my PhD student running something, and he just went in and took 9 nodes. Oh, thank you. That's why it's running. Let's ask good old Patricio if he can give me the nodes for a second. Or let's go ahead and let's be a jerk and just cancel his job for a second. So I'm just gonna warn him. I'm just gonna warn him real quick because Pato, un segundito, quiero hacer otro benchmark y tú te tiraste justo a correr una cosa. Te voy a cancelar lo tuyo, pero échalo a andar en un ratito corto. Estoy grabando un video. Ya. So SSH into master mode, and let's go scancel or sudo scancel this job ID and put in my administrative credentials. So being a jerk, I just brought down that job by Patricio, but that's okay for a while. I'm also going to bring down these jobs that are pending. This one and this one. And this one, it seems like those are sudo scancel like this. What is Patricio saying to me? This is fun. No. Okay, good. So I'm not gonna bother Felipe. Felipe is another student that's running a model, and that's been running for 1 day and 11 hours. So I don't want to mess with that. Okay, so let's tell OpenCode over here a few things. So let's go like this. The 10 GBE fabric is being used for storage. So Kraken chest or the Kraken server is using the 10 GB link, and it's also used in the master node for the Deadman chest local storage writing. So that Deadman chest is an NVMe, which I should be able to write at full speed through the network, and this is something I want to check. And Kraken is a RAID storage. So I want to see if I hit the RAID bottleneck or I hit a network bottleneck when writing to these machines. Let's go. That's me using voice to text. to instruct my cluster what to do, which is super exciting. Okay, there it's looking at my disks. It can see that Kraken is inside, it's being network shared, whereas Deadman's Chest is a local, at least for this machine. Okay, now I see the stored architecture. It found out that that's a 4 terabyte NVMe that is local. It's local to the main machine, but it's not local to the compute nodes. Kraken, on the other hand, is a separate machine. And then there's this here, exactly, there's Leviathan chest, which is another one. It's a 16 terabyte local on master. Okay, so what does it want to do? It wants access to all these things. Let's just allow. Let's just allow, baby. I'm going to interrupt for a second. What I want to measure is the write speed through the network from the compute nodes. So it doesn't matter what's going on in Maestro at Esmeralda. I want regular MPI jobs writing, being run through MPI run on the Slurm and writing to Deadman's Chest, which is the main node, or writing to Kraken. Let's see what our IO performance looks like. It didn't get on my message. I want regular writing being run through MPI run on Slurm and writing to Deadman's Chest, which is the main node, writing to Kraken. Let's see what the compute nodes can achieve in terms of performance writing to Deadman's Chest or writing to Kraken. Kraken. It should be able to figure out what I'm trying to say. It should be able to figure out what I'm trying to say. Hello, one viewer. As it's going into this, it's going into the nodes, I guess, and taking a look at the check mounts log, whatever that is. I have no idea what that is, but it's looking into my system. It's looking at the job status. It's running some command. What is it going for? There, you could see it tried to run something for a little while. So I saw the queue. I saw the queue do something real quick, but I missed it. And now what's going on? You have full access to my cluster. You could do anything you want, little AI. Let's see what it comes up with. I'm streaming for 12 minutes. This should be fun. Yeah, this opens, having open code. I just installed open code on the cluster and made it available, and it's now taken over my cluster. This should open some pretty exciting possibilities in terms of the workflows that we can have with the students to do the research and myself. There's some admin duties that are going to be much easier now that open code can take control of the cluster. What is it doing? Benchmarks, check mounts. Wait for the check mounts. No idea what it's doing. What is that check mounts command? No idea. I guess it's requesting some mount data. So what the compute nodes can see in terms of storage. Okay, now we know the layout. That's exactly what it's trying to figure out. Deadman's Chest. That's our node list, so it knows the layout and NVMe on master. You can write at that speed and then rate on Kraken, permission denied, deletes write access, NFS share, which is 2 gig per second, is way below 10 GB capacity, but is within the 2.5 gigabytes per or gigabits network. So I'm writing at least to Deadman's Chest. I'm writing at and NFS share should be the same thing. It's going through the 2.5 GB links. So this is what I expect the performance to be like. The large-ish 10 GB connections to Kraken, they're there so that we can write in parallel to these nodes. What is going on? I don't know, it's going crazy now. MPI storage. So it wrote a bunch of C into benchmarks, and now it's trying to run something else. Look at that, compile storage benchmark. It's compiling a new storage benchmark. It's coming up with it on the fly, and it's going to submit that. And you can see there it goes. That's amazing. It's using Slurm to, it's got all these jobs. And why aren't these going through though? These are, okay, one is completing. This should be waiting for the results to check. So it's running all these benchmarks. It's running stuff. It gives them some nice names, and you can see my user being used, and it allocated 1 node, 4 nodes, 8 nodes. This is so cool. This is insanely cool. So I don't know how long these benchmarks are going to take. Let's exit from here and go into my user. Just take a look at what it's doing. Let's see if we can do that before it finishes. So SSH, JLE, going into the new benchmarks folder in here, and we have the new benchmark that it came up with. Should be network sweep. It's called check mounts analyzer. Which one is MPI storage? Is it this one? I think that's the one. MPI storage. So let's see. MPI storage.c, and it's now thinking. So what is it doing? MPI abort. I'm trying to figure out what it's doing. So it's writing stuff, but I guess this is output. So it's opening a file and snprintf. I have no idea what's going on. So it's writing a bunch of stuff. This is a warm-up run, writing a bunch of stuff to the disk, and then after the warm-up, it's writing some more stuff, and it's writing up. Yep. So it's doing, obviously it's doing some writing and then some reads through the network to see what the performance is. And that's what it should be doing, but this is so cool. Let's take a look at what it has to say about, let's see the benchmark. So run storage.sh. So this is the one that probably spawned all those jobs on the cluster. So storage target, dead man's chest, and this chunk sizes. This is probably to write different chunks or different size payloads. So megabytes from 2 to 256 megabytes, and how many iterations to do. You need to do iterations because it's a stochastic thing. It's non-deterministic how much it's going to take. It keeps on launching jobs. This is amazing. How many jobs it's running in my cluster. And then here we go. So what is it doing now? What has it? Now we have the key finding. Compute nodes have only 2.5 GBE. The 10 GBE Intel NICs are only at the master and Kraken. This explains everything. Well, this is what I told you at the start, right? Let me resubmit the storage benchmark with proper labels so results don't collide. Okay, so it had some colliding results. So it figured out what I told it at the beginning, but now it inferred it all by itself. That's all the code it generated. Let's see what else we can see. This is very revealing. Let me take a look at the logs some more. Okay. It keeps running benchmarks. It keeps doing stuff. So what I'm going to do with this is I'm already seeing that for the writing, I am being bottlenecked by the network, at least in Deadman's Chest. Deadman's Chest is an NVMe drive that is located in the main node. So I can write to that disk at network speeds, not at NVMe speeds. What I want to see, so basically I would benefit to writing into that disk by upgrading the storage. Already I can have a benefit. My real question is in Kraken's chest. Kraken's chest is a RAID drive. It's a RAID machine. So I want to see if my RAID configuration, which is a RAID 5, if that RAID 5 configuration is fast enough to accept input data transfers at network speeds. If that is the case, then I'd benefit from network increase and also going to NVMe drives for the large storage. Otherwise, I just might need to upgrade the network and just see performance increase by that much, just the network. Now, a network, I'm looking at some NVIDIA switches to get 25 GBE speeds for the compute, so times 10 this. And for the storage, it might be 100 GBE actually. But this will require special cabling and special layouts and a very expensive equipment, which we have money for. It just keeps going. Look at it. Look at it. What is it doing now? So it's looking at Dead Man's Chest with 4, 2, and 8 nodes, and Kraken with 8, and it's taking at least some more time, I guess, with Kraken. It's checking the disk in Kraken and in Dead Man's Chest. Again, that's my layout. That's my layout. If you take a look, let's exit. But if I go df -h, you'll see Kraken's chest is mounted through the network in a physically separate computer, and that's going through the 10 GBE links. Deadman's chest is local. So Deadman's chest is this guy over here, and this is a local NVMe drive. And then I also have Leviathan chest, and that one is also a local drive that is also shared through the network. So if I go into one of the nodes, I can't do this from this account. Let me go into the master account like this, SSH node 1, for example. And if I do df -h in the master node, now you can see what a node looks like. So Deadman's chest is available, but it's going through the network, through the master node. And you can see also our shared and Leviathan's chest, and we have a bunch of stuff, a bunch of storage. But from the node point of view, from the compute node, we only have 2.5 GBE links everywhere, right? So that should be our theoretical limit as far as the network goes. What I want to see if that's our bottleneck, and it is for Deadman's chest, it is for these three, it should be. But my question is this guy over here at Kraken's chest. Is Kraken bottlenecked by network? And if it is, that's a bit of a good news, because I can get a good performance upgrade just by upgrading the network. So let's see what these benchmarks are doing. It has a whole bunch of benchmarks that it's running. What else can we do with an AI agent model running in my cluster? I can do all sorts of stuff. So parametric studies. So parametric studies with large finite element models. That would be a thing I would do. Like I want to figure out what a given parameter for a finite element model, what's the best parameter for that? Like just go crazy, run this model, just change this parameter, monitor the output. Or if something goes wrong with the simulation, it can restart the simulation with new options all by itself and just leave it running. This is really, really, really cool stuff. It's almost done. There we go. There we go. There, I can see some jobs pending still in the cluster, but it already has some stuff. So let's read this together. Network topology discovery. This, just by manipulating the cluster, it realized that the compute nodes all have the 2.5 GBE link, whereas Esmeralda and Kraken are going through the 10 GBE link. That way we can write in parallel, theoretically. And then MPI point-to-point, 90% of 2.5 GB theoretical max. So we are good there. We are using our network well, at least for the point-to-point communication through MPI. Storage benchmarks, here we go. So Deadman's chest, we have that. So we read speeds are purely page cache in our, okay, bottleneck diagnosis. Per node bottleneck, 10 BG, 77% efficiency, aggregated bottleneck. We get up to 8.4, so that's 84% efficiency in the 10 GB link. That's good news. Now storage backend and BME local, I can write, not a bottleneck, RAID not a bottleneck at this scale. So I can write, this is something new for me. I can write at 1,000 megabytes per second to Kraken. So you hit the network before you hit the disk. Each compute node is limited to that. The storage server, 10 GB link, then limit the aggregate throughput. Okay. And Nord Kraken RAID is the bottleneck at these job sites. To go faster, aggregate writes to multiple storage targets or bonding across the 2.5 GBE interface if the nodes all benchmarks source code. So the conclusion, I just asked AI to tell me where my bottlenecks are, and it told me network is a bottleneck right now. You're not, neither in compute or in IO, I am hitting network limits. That means for my setup, at least for these MPI jobs, I can just get a performance boost by upgrading the network. And that is exactly what I'm going to do. I'm going to buy these NVIDIA switches to go to times 10, basically the compute nodes. So they go all the way to 25 GB. And then the writing for the storage is going to go to 100 GB, God willing, in the next few months. That's all I want to report for now. See you guys next time.